On 3, Introduction to Selection Problem. We have solved a special selection problem. Find the minimum of an unordered array. For this, new topic, we will solve a general selection problem. So our problem number 15, the general selection problem. So let me describe it first. Given an array and a positive integer k, all right, k, then we want to find the kth smallest element in the array. This array is unordered. Yeah. We assume it is unordered. Otherwise, if it's ordered, it's trivial. You just count from the left, kth smallest. So you don't not need to do much work. Yeah. But for unordered array, it's not that easy. You need to do a lot of work. Yeah. So now we need to solve this challenging problem. All right. First, we have a name for this k number, kth smallest. So we call it kth order statistic. Kth order statistic. So we give it a name. And then there is another name, we call it rank. The rank of this element is k. Kth smallest. Yeah. In different contexts, so we may use different names for it. All right. So let's do some analysis. First, we know the data is unordered. If it is unordered, the natural question is, should we sort the array first? Right? Sometimes, for some special questions, it may be a good idea to sort the array first. Look at our element uniqueness problem. We can sort it first. Element uniqueness problem. But here, the situation is different. So let's look at the cost. If you do it, how much cost do you need to pay? Here, the general situation, the cost is big theta of n log n. Although this result we haven't learned at this point. Later, we need to learn more sorting algorithms. We will get this result. Now we just borrow that result. Borrow that result. The average case. Here we talk about average case. Okay? Yeah. All right. The question is if this cost is acceptable or not. It depends. If we only look at this problem, original problem, this cost is too high. We don't want to pay this much cost. We can do faster than that. Actually, we can solve it using big theta of n. We can drop that log n. So that's a pretty good improvement. If for this particular problem, original problem. But why I emphasize that? Because if I modify this problem a little bit, okay, then the answer could be different. If I ask you, still selection problem, but we need to find large number of elements with different rank numbers, then the story will be different. Not just one, many. How many? So we don't know. Certain number. When you reach certain number, then it could be a good idea to sort it first. Yeah. So that's something like you make investment. Okay? So this is your investment. After you make this relatively big investment, you want to use it more. If you only use it once, it does not. So your investment is bad. Not worth it. Yeah. Not worth it. Yeah. But after you make this big investment, then you use it many, many times, then it's worth it. It's a good investment. So the same reason. All right, so here, but this one, we target this performance. Okay. So that's why we want to avoid the sorting step. We cannot do the sorting step. All right. Next, how do we divide the problem? So that's the most important problem for this question. If we can answer this question, then we pretty much solve this problem. All right, so let's look at the idea. Divide and conquer. First, divide the problem into two subproblems, two smaller subproblems, just like our binary search. Right? But here, much harder than the binary search. How to divide? It's not that easy. Yeah. After that, drop one of the subproblems. Drop one of the two subproblems based on the elimination criteria. Yeah. The rank, we can look at the rank, so we can drop one of the subarrays. Yeah. Then, next step, convert the original problem to one of the subproblems. Yeah. Because you reduce the problem size, after you reduce the problem, you need to make some adjustment. Okay? So that's why you need to do that adjustment. So you may need to do this specifically. The original case order statistic, you may need to do an adjustment of order statistic. Why? Why? So you will see easily. You will see easily. Yeah. Yeah. Two subarray. Yeah. So left subarray, right subarray. Okay. Yeah. So you will see that. If your element falls to the right subarray, you need to make an adjustment. If it falls into the left subarray, you don't need to make an adjustment. Yeah. I will explain this later. At this point, we do not have enough information, so we delay this part to the next video. Last one, 3.4. All right. Elimination idea. So when we consider the elimination idea, there are two cases we can do the elimination. The first one, eliminate from left end. We do elimination, so array you have two ends, left end, right end. You can do from the elimination from the left end, that means the smaller end. Okay? The minimum end, the larger end, larger side, the maximum end. You can also do elimination. Yeah. So from the right end, yeah. The two cases like this. Left end, this red circle part, right end, that red circle part. Okay, all right. So then another view for it. For each element, there is a rank, right? So if you select one element here, let's assume it is the k smallest. The same element, if you look at from the larger side, you can count what is the right, yeah, counting from right. how many elements larger than that? Or what is the, if we want to know what is its x largest, what's that number? X largest, right? We can also view that way. For example, when k equals 1, 1 means smallest element, first smallest element. But if you from the larger side, that will be the nth largest, right? Yeah. Nth largest. Smallest equals nth largest, okay? All right. Second smallest corresponds to n minus 1 largest, right? Largest. Okay. Third smallest corresponds to n minus 2 largest, right? So you can get that. Okay? All right. Now, remember, I introduced that invariant method. Find invariant. That method. Here, can you find something invariant? 1 plus n, n minus n plus 1. 2 plus n minus 1, also n plus 1. 3 plus n minus 2, also n plus 1. Is this n plus 1 invariant? Yeah. So with this n plus 1 invariant, this invariant concept. Now I ask you, you have a kth smallest. If you look at from the larger side, what is that x? X largest corresponds to kth smallest. So k plus x equals invariant, a plus n plus 1, right? Yeah. So that's why x equals n minus k plus 1. So that's how you find that number. All right, so this is our part D.3. We have last video left, 8.4. We couldn't complete this topic because I spent 2 videos covering 6 questions in homework assignment number 1. So we need to spend another class to complete this topic. All right, so let me stop it here.